Hi, everybody. Last time we were talking about two-phase line followers, how they work with intersections, and I mentioned that we would start talking about proportional line followers. Well, in order to really understand how a proportional line follower works, you need to take a really in-depth look at how a two-phase works, and it will help you understand what's going on with the proportional line follower. So let's take a look at how this works. So we were running this one before, and it will grab the line and do some line following. It's going to make its way. It's going to do okay. If you did any experimentation, you may have discovered that if you increase this number, like let's say to, we'll just go up by 10, so negative 60 and 60 here. The robot's still going to follow the line, but it's going to do so a little bit slower. And if you change it even to be even more tight like this, it's going to be even slower still. It's still following the line. It's just doing that at different speeds, different overall speeds. So we know that as this number gets bigger, the robot gets slower. So you might say, well, let's make it a smaller number then, like 40. Now the robot is going to have a hard time grabbing onto that line. We'll run it again. Now, the reason that the robot is having such a hard time grabbing onto that line is that it's not being told to sort of yank the steering wheel over in the direction of this line enough. How do we know that? Let me show you what happens if you run this 40 number on a different part of the board. So what if we took it over here to where the curve is less harsh? All right, so what if we ran that 40 number over here? All of a sudden, the robot will follow the line. In fact, it will be able to handle this gentle curve here. But if I use that same number on a more curvy section of the board, the robot will be able to make it through the gentle curve, but when it gets to the sharp curve, it's going to lose the line and end up crashing into the wall. So we have sort of two different needs here. We want the robot to go fast, so we want this number to be like really gentle. But we also want the robot to stay on the line, so we need this to be really high. So this needs to be different in different situations. When the robot's on something smooth, we want this number to be really gentle. When it's on a sharp turn, we want it to be not so gentle. So how do we figure out how that works? All right, so if the robot is completely on the light side of the line, it's completely over on this side. If it's gotten this far, it needs a really sharp turn to get it back onto the line. If it's only off just a tiny little bit, like there, it does not need as hard of a turn in order to get it back on the line, right? So let's think about these two states. In this one, we are seeing 100% of the light is coming back to the robot. So we need, if it's at 100% light, we need it to sharply turn towards the line. If it's here at 80, we don't need it to move as sharply towards the line. If we're somewhere like this, well, we barely even need it to move at all. So how can we do that? Well, there is a whole different method of getting information from the sensors, and I'm going to show you what that looks like. So in the yellow section here, you can grab a color sensor. And when you grab this, it works differently than it does in the switch. We're going to change this to measure reflected light intensity. Now, this is a block that gathers whatever this number is wherever the robot is at that moment. So I'm going to completely remove this two-phase right here and think about this. So if I have this number, right, if the number is really, really off the line, it needs to turn sharp in. If it's close to the line, if it's like right on the edge where it needs to be, it doesn't need to turn as hard. So here's how you do it. There is a number that is like the perfect number between this, which is 100, and this, which is 0. And I like to use the average of the two numbers. So let's say it's 50. So if I take what the current value is and I subtract 50, let's think about what that means. If I'm here, it means 100 minus 50. That's 50. If I'm completely here, I get 0 minus 50, which is negative 50. All right. Let's imagine if it's somewhere in between. What if it's, whoop, that's too close. What if it's at like 84? 84 minus 50 would be 34. So it would move in, but not as hard as it would if this were at 100. So you got to think about what the robot is doing at different times. This number that we're calculating here, this number sort of represents how far off the line we are, right? If we're really far, it's a big number or a big negative number. If we're close to the perfect spot, it's a very small number. So let's take a look at this one, 48. 48 minus 50 is negative 2, so it's a very small number. So think about what that means. If the robot's really off really far, it gives us a big number. If the robot's off just a tiny bit, it gives us only a tiny amount. Well, we can use that. We can use that to steer the robot. Because remember, the steering is a number from negative 100, which means extreme left turn, to positive 100, which means extreme right turn. So what if we just took this error and we plugged it in? I'm going to slow the robot down so we can study it. We took that error and then we let it be how hard of a turn the robot does. That means if the robot's really off course, it's going to turn 50, right? 100 minus 50 is 50. It's going to turn 50. If it's way in the dark, it's going to turn 0 minus 50 is negative 50. It's going to turn really hard the other direction. But how hard it turns depends on how far off the line it is. So the amount of steering is proportional to how far off the line it is. That's why it is a proportional line follower. Let's take a look at what that looks like when you run it. So if I just do this, nothing else, whatever the sensor sees, minus 50, plug that in to be this steering, and we keep it slow. Let's see what happens. There it is. It's following the line, just with that. Now, let's move this up to the same speed we were running earlier. Let's take a look. It's actually going a little bit faster than when we were doing it before. You could still see the wobbly motion of it, but it's going a little bit faster than when we ran it at 50% speed before. That's because when it's on a straight section, it's not going to be far off the line, so it's using less of the amount that it needs. All right, now we can add one more piece of this to make it even more customizable. So check this out. Let's add another math block in the red section. So I can take whatever this was and I can multiply it by something. So if I take whatever it sees minus 50 and then multiply that, let's say by 0.5. Let's think about what that would do. Let's think about the math. All right, so if we're completely off the line, we're seeing 100. So let's calculate what the robot's going to do. 100 minus 50 is 50 times 0.5. That means that this is going to be 25. So a very slight turn on the way in. Now, if it was completely on the line, 0 minus 50 is negative 50 times 0.5 is negative 0.25. So this number can be used to adjust how hard the robot is turning into the line. So with the error calculation, we can have the robot be faster when it's more accurate and slower when it's on a curve. And with this, we can make the overall push of this is a curvy course, so you need this number to be as high as possible. You could even increase it higher than 1, right? If you're on a curvy course, you would probably want this high. If you're on a relatively straight course, you might want this number lower than 1. And you can change and alter that. This is a proportional algorithm. There are different parts of it. This is called the error, and this is called the constant of proportionality, because it determines how it's a constant, it's a number that you're multiplying it by, and that number is what determines how hard, what kind of proportional turn it makes into the line. So when we run this all together, let's see what happens. So 0.9, it fell off the line. At 1, it'll grab it and go. At 1.5, it'll go, but it'll go slower because it's going to be doing that zigzag back and forth thing too much. So you see that this number is what sort of limits or sort of directs how hard this turn is, and you can change it with just this one number. That's the constant of proportionality. All right, I think that's going to be it for proportional line followers for this time. We will talk a little bit more about how all this actually relates on a WRO board next time. So I'll see you then, and have fun and happy coding.